Hello, everyone. Hope you're doing well. Last time we were seeing a lot of different examples of this new type of space called a metric space, which could have a lot of different things as some of its items, its objects that in which we are taking our metric, things like numbers and vectors and RM and things like this were already involved. We also saw functions and sequences, however, and we even saw a way to take arbitrary sets that could be sets with anything in them and apply something called the discrete metric to them. So there's a large and more general class of metric spaces than there are with the types of things that we are more used to. Things like trying to make convergence happen in RM is a different story than trying to make convergence happen in a more general metric space. But what we're going to see is that there's a lot of parallels today. We're going to get to talk about a lot of the different ways that we can connect some of our intuition when it comes to vectors in RM and how these things converge to other vectors. And then try and see how metric spaces follow a very similar code. We'll talk a little bit about some of the geometric intuition, about how we can say these things converge, and then we'll end out with a bit of a diversion here of something called little LP spaces. We've already seen some examples of things like little L1, little L2, little L infinity. And you might have looked at those and thought, well, those are interesting names for each of those things. Are they connected in any sort of way? And we'll say, yes, these things are specific examples and oftentimes the most used examples amongst other types of spaces known as little LP spaces. So we'll end the day out on that. But for now, let's go ahead and get a definition of convergence in a metric space. Our example on slide 8 of the previous video lecture, that was this one that had to do with you had a sequence of functions, f sub n, and you were looking at little spike functions. These are sometimes what these are called, spike functions of this form. And we talked about how some of the functions had different distances from the value of 0 than others. Right. So for example, and we'll see this in a future one because I went ahead and worked out that a d sub 2 example to see that the distance from f sub n to 0, I believe we calculated to be, I think it was something like 1 over n. The distance for d sub 2 for f sub n to 0 is the square root of 2 over 3n. And then finally, d infinity of fn 0 was equal to just 1 for all n. So notice that this means something interesting for us with divergence, because we could ask the question, do the functions f sub n approach 0? Well, now the question arises, in what sense do we mean that they approach? Do we mean in the sense of like maybe the highest point and the lowest point eventually grow closer together and they meet? So something like in terms of the d infinity metric. Or do we mean just like that the area underneath these functions grows to go to 0? So the same area as 0 would, or that the two, when subtracted, get closer and closer in area to 0 in their difference. Or maybe even there's some sort of square that you want to imply there, kind of like in a similar way to the Euclidean metric. You're doing some little bit of action here with d sub 2 and saying, oh, well, I want to square things first and make it like an actual distance formula where each point is having its own weight of distance before we take that infinite sum, the integral, and then square root. But let's make sure that we know, okay, how those sorts of convergence things work. Let's see how these things are defined. Let's first take a metric space, x comma d. Remember, a metric space for us is a set together with a metric function d. And we'll see a sequence x sub n and x converges to a point a inside of x if for every epsilon greater than 0, there exists an n in the natural numbers, such that whenever n is greater than or equal to n, the distance between x sub n and a is less than epsilon. Let's talk about some of the similarities here first. Notice that this is almost exactly the definition of convergence in RM. The only difference is that we have substituted out our absolute value notion of distance with a more general one, the distance that is on this metric space, the value of d. So there's no more subtraction going on. Notice we're not taking x sub n minus a or anything like that. In fact, in general, although many of our examples have notions of plus and minus, you can think about in arbitrary sets, you don't even need to have a plus or minus defined between two vectors. Take, for example, the set x being the arbitrary set, and you're looking at the discrete metric. Well, you could actually have just the set x be triangle, square, circle. right? Something like this, some arbitrary collection here in which you cannot think about subtracting the two values or adding any two vectors or anything inside of that set. So the only thing that we can do then is that instead of taking delta minus or triangle minus square, we would have to say, okay, the distance function on triangle and square, if this is the discrete metric, then this one would be equal to 1, for example, whereas the distance between triangle and triangle would be equal to 0. So this is using that as its substitution. So we've taken out this notion of subtraction between two vectors in Rm and replaced it with just the distance function plugging in two separate values in the space of x. And that's what we want to be less than epsilon past the cutoff points at capital N. After that point, everything there is the same. Notice now that these distances that we're getting are interesting in terms of how they think in terms of convergence. Looking at our functions of f sub n, like from up above before, it looks like some of our d1, d2, d infinity functions could actually have these be converging. Is it the case that f sub n converges to 0 for each of these metrics? Well, it should for the d1 metric, because d1 f sub n comma 0 is going to be equal to 1 over n, and that is a value that should converge to 0. So eventually, once we get down what f sub n is in terms of the value of n, then we should be able to say, okay, we can just think of this as a real number sequence now, where the d1 values are just going to be equal to 1 over n, and we know 1 over n goes to 0. Hence, this function's f sub n should converge to 0. Notice that d sub 2, we could say a very similar thing, although it's a little bit trickier because we don't have something on the level of 1 over n. We have something on the level of square root of 1 over n. So we'd have to have some sort of statement that says, if this m1 over n sequence converges, then so does 2 over 3n, and then hence so does the square root of 2 over 3n. So we'd want to be a little bit careful there in how we write that out. But notice that this last line says that the d infinity metric, f sub n and 0, are always a constant distance of 1 away from each other. That means that in the case of the infinity metric, f sub n and 0 are going to always be a constant distance of 1 away. There's no way for f sub n to converge to 0. And the reason for that heuristically is that at this point here, the function f sub n is always equal to 1, and the function 0 is always equal to 0. The supremum of all possible differences between the two functions at any point is going to always equal 1. So we cannot say that the function converges to 0 with respect to that metric. Now that we're being a little bit more relative about what metric we're talking about, this becomes a little more interesting in terms of its definition, talking about how things are supposed to approach certain other vectors or values or functions, right? Thinking about this set right over here, x equals triangle, square, circle. What kinds of sequences in this set are going to converge to any other set? Why don't we think about that actually? How does convergence work in the discrete metric? Let's let x be a set and let d be the discrete metric on that space. And let's assume that x sub n converges to x in x comma d. So we've got some collection of values inside of the set x that do converge to x. Well, what is that going to mean? We need it to satisfy the definition given up here. That is, for all epsilon, there exists a cutoff point so that the distance between that sequence and the value of x is less than that epsilon. Now, that needs to be true for all epsilon. And something interesting about the discrete metric is that you can only take on the discrete metric can only take on values of 0 or 1. So we can kind of force the issue here a little bit and say, okay, let's make epsilon equal to 1/2 for this definition. So we know that there needs to be a cutoff point in this sequence. There needs to be some capital N so that whenever n is greater than capital N, that the distance between x sub n and x is less than 1/2. Well, how are we going to make that happen? Well, again, the function can only take on the values, the distance metric can only take on values of 0 or 1. This is going to imply that dxn and x actually has to be equal to 0 because there's no in-between value here. But what does this mean? X sub n is going to have to be equal to x because that is exactly what it means to be the discrete metric. The only way you can get the distance to be 0 is if the two values that you're putting inside of the distance metric are equal to each other. So we're saying that there is some sort of cutoff point so that x sub n is equal to x for everything past that cutoff point. The sequence x sub n must eventually be equal to the value of x. Notice the stark contrast to this in terms of Rm. There, a sequence never has to equal a point in order to converge to it. But in the discrete metric, the sequence only has finitely many entries, those that are to the left of the cutoff point, capital N, that we described before, which are not equal to it. So we will sometimes use little bits of intuitive terms to try and help us make sense of this. We'll sometimes say that convergence in the discrete space is very hard. You can be as close as you want in another sort of sense, maybe in a proximity sense, to a given point inside the discrete metric space and never be able to converge to it, right? If you're never equal to x, then you can never converge to x. So that makes it very difficult, very hard to converge inside of the discrete metric. On the other hand, convergence in Rm is a lot easier than convergence in the discrete metric because as long as you're just picking your points and having them be, geometrically speaking, in our intuition, closer and closer to this point x that we're converging to, then the x of n should converge to x. But remember that, again, we're thinking about changing our geometric intuition here based on what the metric is. Recall again that in the discrete metric, we're saying that every point is somehow distant 1 away from every other point. So we're saying, okay, here is a point x that I'm having this converge to. Any other point inside of this space, and that could be Rm, that could be everything else. This whole space, which you could think of as just maybe Rm, take out x, is all of distance 1 away from the point x. If we move to another point, then it's kind of like a fisheye moving and focusing in on that one point. Everything else just kind of being far away from it as possible. And in fact, the exact same amount of way. So there's a little fisheye lens going on there. As you focus in on one point, every other point is a distance 1 away. It goes in at the rim of the fisheye, and then you move up to another point, and now every other point's at the fisheye, so on and so forth. So that's the kind of the way our geometric intuition has to shift around when it comes to these new metrics. And so convergence in these metrics can be a lot harder or easier than we would anticipate. So let's solidify what we were talking about in our previous slide. For which of the metrics of the f sub n metrics that we were talking about up above, does the sequence of functions f sub n converge to 0? Over here, I've gone through and calculated how we found the value of square root of 2 over 3n for the distance sub 2 of f sub n comma 0. And you can see kind of here where I went through and did that. I just was taking integrals of squares of these functions and then taking their square roots after taking the integral. Notice here I used a couple of different expressions here to kind of simplify things out, especially going from this step to this step. I broke things apart into even versus odd functions in order to make it easier to figure out how to get everything in terms of one integral before going off and doing stuff. And that's when I ended up calculating out everything and getting square root of 2 over 3n for this distance. Well, so the distance 1 of f sub n to 0 was equal to 1 over n, and we know that this goes to 0 as n goes to infinity. This means that f sub n converges to 0 in the D1 metric. D sub 2 f sub n comma 0 is equal to 2 over 3n square rooted, and this also goes to 0. Again, we can say probably without any work in our homeworks or anything like that, that 1 over n goes to 0. No need to prove that every single time. But proving something like this was probably a good idea just to kind of keep our epsilon and n proofs sharp. How would you show square root of 2 over 3n goes to 0? You might, at some point, maybe just prove a lemma. If I know that a particular sequence, s of n, goes to 0, then if, say, for example, let's say you say s of n is greater or equal to 0 and s of n goes to 0, then that implies the square root of s of n goes to 0. And if you want to prove that, then that's totally fine. That can be very, very useful here in order to show that this sequence goes to 0. At some point, you might use the fact that 1 over n goes to 0, and you can do that without proof. However, d sub 3, I'm sorry, not d sub 3, d infinity between f sub n and 0, this one's equal to 1 regardless of the n, and this does not converge to 0. So we get that the sequence of functions f sub n converges to 0 for all of these other values, right, except for the value f sub n comma 0. Now, I want you to notice something here real quick. F sub n converges to 0 in D1, f sub n converges to 0 in D2. It does not converge to 0 in D infinity. A wrong question to ask here is, okay, then what do the sequence f sub n converge to? Do they converge to 1 because these distances are always equal to 1? No, the d infinity f sub n comma 1 is going to have the exact same issue. Its distance is always going to be equal to 1. In fact, you could go through and show that the sequence f sub n and the d infinity metric don't converge at all. They don't converge to any function. And you can maybe try and go through and find an argument for that if you would be interested in it. And so, in fact, f sub n does not converge. Hint for that argument that I was talking about from before. Show f sub n is not Cauchy in d infinity. We can think about this definition of convergence that we've just done and alter it slightly to talk about a definition of convergence. You're saying essentially that for all epsilon greater than 0, there exists a cutoff point in the natural numbers such that whenever n is greater than or equal to big N, then this should imply that the distance between f sub n and f sub m, at least with respect to this metric, is going to be less than epsilon. This would be for Cauchy. So to show it's not Cauchy, you would be going through and negating this sort of definition. You could absolutely show that if you'd be interested in it. I think it's a great idea. It helps you see a lot of what's going on here with this function to see that there's a lack of Cauchiness here with this particular metric. So that's because convergence in the d infinity metric is typically harder than convergence in the d1 and d2 metric. Think about how your functions would have to be in order to converge in a d infinity metric. Remember, you're saying that the supremum between the two functions that you're trying to say is less than epsilon. Literally, you'd have to think, okay, your functions are in any part or sliver of that function, they are always like really pretty close to each other, almost like one line sitting across of each other. Maybe one line dips underneath it, the other line at some point, but the two cannot go very far from each other at any given point of x. So d infinity convergence is usually pretty hard, whereas d1 and d2 convergence is a little bit easier. Now, let's go ahead and get some more ideas here for our geometric notions. We've been talking a little bit about how functions converge, and we're going to be focusing a lot on that in the latter half of this class. I wanted to introduce it here as we might see that some in our examples. But for now, we're going to be focusing on other types of metric spaces and how to get understanding of their geometric notions, because there our geometry is a little bit more solid, it's a little bit more firm. It's easier to think about how things might converge in RM. A little bit trickier to think about how things converge in sequences, but because these are just kind of like infinite dimensional RM spaces, excuse me, then there's some sort of limiting process that happens in our geometric sense when we start trying to think of sequences converging. So let's take a look and see how these sorts of things correlate. One, let's imagine that we have our metric space X. Well, if we were going to say convergence happens at a particular point here on a function, we would be saying that for all epsilon, there's going to be some sort of little window here that's for that, so that for whatever values you have inside your little delta window, then your values on this, say, function here that we're having converged to this point are within that little epsilon window. Here we don't get the windows like we do in R2. This is maybe sometimes more generally called a little epsilon ball. Remember how we were talking about the unit ball before? That was going to be kind of like a sphere of unit 1 around a point 0 or something like this in terms of R2. Well, you can think of little epsilon balls in terms of R1 as well. Notice here, first of all, I'm saying that the radius of this ball is epsilon. And since this is a one-dimensional space rather than a two-dimensional space, it really just kind of looks like an open interval around a given point. That's a little epsilon ball. Similarly, here, you've got a little delta ball going around here at this x value of 2 for this given function. And that's what's meant by this little red slot here. In more general terms, or maybe just kind of getting the geometric intuition from R2 here, here is an epsilon ball in R2. Notice that its radius is epsilon. And something that we can be looking at is to check to see if, whenever we're checking to see if there are values close enough to a value of x, we could see if little delta balls fit within the epsilon ball given here in x. So I've been calling these epsilon balls, and the more formal term is the ball of radius epsilon around x, right? So just sometimes it's also written in this form, and in fact, you'll see this sort of formula a good bit. This is the ball centered around x of radius epsilon. So this is what it's centered around. and this is its radius. So the informal way of talking about these sets is that this is the set of all y values inside of our metric space X, such that the distance between X and Y is less than epsilon. So where does the delta kind of get to play in with here? Well, we'll talk a little bit more about that once we get closer to notions of continuity, especially with functions. And we'll be doing that in the next video. These pictures are going to be very important in terms of that as well. But let's go ahead and talk a little bit about sequence convergence a little bit more in terms of this geometric picture. And so another way to describe x sub n converging to A, like we've seen up above, is as follows. We could say a sequence x sub n is eventually in a set A if there is a cutoff point such that x sub n is inside of the set A for all n greater than or equal to n. Picture-wise, this looks like you have, here's your set A over here. It does not have to look like a sphere. It could look like something else. And maybe you have a point. Maybe you have a sequence in here that is eventually going to be inside of the set of A. Well, if this is the set A right here, then after this point, the sequence is going to be consistently inside of the set A. So we would be able to say that this sequence is eventually inside the set A. Let me go ahead and show you, this is an example of eventually. Let me go ahead and show you a non-example of eventually, just to make sure it's clear the intuition behind what I mean here. So let's take our set A once more. Won't be able to draw it the same way, but let's take a different sequence now. Let's say that it's a sequence that looks like this. Notice what's happening with this sequence. I could constantly have points that are either inside and constantly points that are outside of this set A. So although there could be infinitely many points inside of the set A, they are not eventually inside of the set A, because given any particular cutoff point, there's always going to be a value of my sequence that is outside of the set A. That is an example of a sequence that, even though they have infinitely many points inside of the set A, perhaps it is not frequently in the set A, in terms of thinking of this and like how you might say, in terms of sequences in R, you might say, let's take the set A to be the set of all x, such that x is greater than or equal to 0. Well, then the sequence -1 over to the n is not eventually in A. It is not eventually in A because even though there's infinitely many values, namely all of the even values inside of this sequence that are eventually in A, it is not all going to be inside of A past a certain cutoff point. Notice that this is true even if you take, instead of -1 to the n, you take something like, let's say, -1 over n to the n. All right, so something like this will not work either. So here you're getting really, really close to the value of 0 inside of there, and you're getting there rather quickly because of this n to the n business. However, this negative that's going on here is saying I'm constantly flipping in and out of the set of x being greater than or equal to 0. So even this sequence is not eventually in A. We'll give this a different term. We'll say that S sub n is frequently in the set A. And in case you're curious, we're not going to see this term very much, so I'll just go ahead and, instead of writing down the definition, I'll just say it. Frequently essentially means there are infinitely many points of this sequence inside of the set A. The official term is that for all potential cutoff points, there exists another point in the sequence past that cutoff point that is inside of the set A. Notice the difference in quantifiers there. In the definition of eventually, we're saying not for all cutoff points, we're saying there exists a cutoff point such that for all points of the sequence past that cutoff point, the sequence is inside of A. So how could we use this? Well, a sequence x sub n converges to A if x sub n is eventually going to be inside of any epsilon ball centered around that point. And I should be saying not x here, I should be saying the point A. So that sequence x sub n is eventually inside of the epsilon ball centered at the point A. So that picture hopefully is very useful. You're saying that regardless of whatever kind of open ball that I might consider, any epsilon ball around the point A, I'm going to be inside of that ball. Notice that we're not saying here, for example, that the sequence S sub n negative 1 over n to the n cannot converge to 0, because notice that this set A is not an epsilon ball around 0. And for those of you who may be familiar with a bit of topology, it does not even contain an epsilon ball around 0. Notice that around the point 0, if you wanted to contain an epsilon ball, you need to look at all of the points that are slightly positive as well as those that are slightly negative around the point 0. In order to get to that, you'd have to be able to include negative values inside of your set. But A is strictly the set of non-negative values. So even so, the sequence S sub n being not eventually an A, this does not disprove that S sub n converges to 0 still, which it certainly does. So how could we use this definition? A sequence X sub n in a metric space XD converges to a point A if and only if the limit as n goes to infinity of d of X sub n comma A is equal to 0. We kind of used this already in the F sub n example, which is that instead of just going through and constructing epsilons and then doing stuff with dxn comma A and trying to do something in terms of just metrics, we said that if you know the numerical value of dxn comma A, and you know that that value is 1 over n or square root of 2 over 3n or whatever it is, then you can just place that in here and ask, does that limit go to 0? And if it does, then great. Then your sequence X of n converges to A. And this lemma becomes to me a lot more clear to see once you get this notion of epsilon balls involved. So we have from the above that for each epsilon greater than 0, dx of n comma A is inside of the ball from x to epsilon. That is from the notion of looking inside of this distance. That's what it means to be inside of there. So one way to think of it is that if the limit n goes to infinity of dxm comma A is equal to 0, well, eventually it's going to be less than epsilon. You're going to be looking at points that are in here inside of that epsilon ball. So those points are going to be inside of the epsilon ball. And in fact, all points past a certain cutoff point are going to be inside the epsilon ball. That's exactly the definition of being eventually inside the epsilon ball, which is exactly the definition of convergence that we were looking at from before. So all of this kind of connects together with these definitions of convergence, one more geometrically slanted and one more algebraically slanted. Notice that you might want to use this one whenever you're trying to visualize what's going on, and you might want to use this one over here whenever you might want to try maybe doing a triangle inequality or something like this. You'll say dxn comma A is less than or equal to, and then you'll introduce another term or something like this and show eventually that your terms become less than epsilon. We're going through like that. So both of these definitions are very useful and offer different perspectives for us in terms of convergence inside of a metric space. Now, I went through and went ahead and wrote, for the sake of time, the solution to this problem in our slides. I've got another problem down here that will work on the next slide. But this is a problem that I find surprisingly useful, but is sometimes not shown in advanced calculus or analysis on the real line courses. This problem has us characterizing convergence of sequences in terms of convergence of subsequences. You may remember I mentioned previously before that there's sometimes an interesting tip you can use. A sequence converges to a point x if and only if every proper subsequence of that sequence converges to a point x. This is a slight variation on that theme. This problem says this: show that if every subsequence of x sub n has a further subsequence that converges to x, then x sub n converges to x. Picture-wise, what's going on here? Let's say you have a sequence x sub n. And you don't know much about the sequence x sub n to begin with. You know that it's got a lot of stuff going on here. But let's say that, for example, you're able to pick every single, and for any subsequence that you might pick for that place, if there exists a further subsequence that converges to, say, a specific number. So maybe you're picking this as your subsequence, and then what's circled in green is your further subsequence, that these converge to a specific number. If that is true, regardless of the subsequence that you choose, that you're able to find a further subsequence that converges to x, then in fact you can say something about the whole sequence in red itself, namely that the entire sequence of x sub n converges to x. Notice how this is kind of a pretty strong property. It's doing a little bit of that local versus global gluing that we were talking about from before. Remember that subsequences don't necessarily have to describe the behavior of an entire sequence at all, not when taken by themselves. We've talked a little bit about how when you take the sequences of -1 to the n plus 1, sequences like this could just, some subsequences like those with odd indices versus even indices, just take you from 1 to -1. Right? Or if they just go 1, 1, 1, 1, 1, or -1, -1, -1, right? And those subsequences can converge, but the whole sequence itself does not converge. But what's interesting here is that we're gluing this notion together by saying not just any given subsequences, but every subsequence of x of n has a further subsequence that converges to the exact same point. Notice that this x is not reliant on the subsequence that you've chosen. It's simply saying that any subsequence has a further subsequence that converges to the point x, this x being something that is irrelevant to the subsequences you are choosing. If you get something like this, then that kind of glues all of these subsequences together. It tells us if every subsequence exhibits this property, then the whole sequence exhibits this property. A quick just walkthrough of the proof with this, you might be surprised or not surprised at how brief it is, given its kind of like complexity in terms of how it's trying to pick apart this notion of convergence. But again, this sort of problem in its proof is somehow useful to us and will come up more often than we expect in some of our theorems as we move along. So I'll go ahead and show it here in case you haven't seen it. We'll go ahead and prove by contrapositive. Remember that the way the contrapositive works is that you're going to start by saying x of n does not converge to x. And then you want to say, well, we want to show there is some subsequence of x of n, such that any further subsequence doesn't converge to x. That's negating this kind of antecedent part of the conditional, is saying there exists some subsequence of x of n such that any further subsequence of that subsequence doesn't converge to x. So if x of n does not converge to x, then there exists an epsilon greater than 0. This is us negating the definition of convergence here, such that for all possible cutoff points, there is some n greater than big N, such that the absolute value of x of n minus x is greater than or equal to epsilon. Something to note here is that I did this in terms of the absolute value notation, since we're a bit more used to that. But we could have very well substituted out with dx of n comma x and written that in here instead. And so we could have just said the exact same thing as we would have in terms of the real numbers. Nothing that we're using here requires us to use this subtraction or anything else with regards to that. So we could have just done this in terms of a general metric space as well. First, now we're going to start constructing our subsequence of x of n. And we're going to call that like this. You may have seen this notation x of n k before. We'll use that notation here. First, let n equals 1. Then let n sub 1 be the n guaranteed by the statement there exists an n greater than 1 such that the absolute value x of n minus x is greater than or equal to epsilon. Then let n equal, this is n sub 1. This is n sub 1 right here. And let n sub 2 be the n guaranteed by the statement above, namely that there is some n greater than n1 such that the absolute value of x of n minus x is still greater than or equal to epsilon for anything past that point, or rather for just that particular n. We're going to continue this process by plugging in now n sub 2 in for big N, and then getting an n sub 3 from that. Then plugging in n sub 3 in for big N, getting an n sub 4 from that. Notice that these indices for the subsequence we're choosing are constantly getting larger and larger, and that we're always able to find a new one by the fact that we could do this for all capital N in the natural numbers. So if we continue this process, we'll be able to continue it infinitely and get a subsequence x of nk such that everything has this property. X of nk minus x, or the distance between these two values, is greater than or equal to epsilon for all k. I'm going to claim that this is the subsequence I desire. That is, if you try and take any further subsequence of this sequence x of nk, and when I say further subsequence, I mean something like x of nk L or something like this, right? So you are saying, I'm going to take that subsequence and take another subsequence on top of that. Then I'm going to claim that that cannot converge to x. Well, indeed, those are elements that have this exact same property. That is that x of nkl cannot be epsilon close to x. But since they can't be epsilon close to x, there's no way for them to converge to x, because eventually you'd have to get to some sort of cutoff point so that every element inside of this subsequence is within epsilon of the value of x. Notice that we've now gone through and proven the contrapositive of this statement, which gets us to proving this statement is given in the problem. We'll see this tool come up every now and then. I'll try and reference it and tell us this is on slide 5 of this particular notes, but just a kind of a thing to kind of keep in the back of the arsenal. But let's go ahead and take a look at another subsequential convergence. This one's not related to the previous one, but I want us to take a look here a little bit at terms of subsequences. The taxicab geometry construction we talked about last time, I describe a little bit here, and we see the subset L1 here as well. Notice that sometimes I will write L1 like this. I see some textbooks do this, whereas sometimes I see L1 written like this. You might see me kind of write some of both whenever I write them. And I'm not going to make a distinction between these two things. These two are the same thing, L sub 1 and L to the power of 1. I think typically we're going to be able to see it more often in this former sense. So the way I've written it here in this problem is the more typical one. But again, you'll probably see me write it in terms of this sense over here on the right-hand side. I'll say the reason is when I was taught these particular spaces, the things were given up there in the little superscripts instead of the subscripts. So it's a little bit back and forth to how authors actually like that notation. Let's fix a sequence in little l1. Remember here, x is a sequence of real numbers. And let's show that the sequence, this is called x to the k, or rather x with in parentheses k to denote that this is an element of a sequence. So this is the following sequence in L1. Let's say, for example, I'm starting with something like this. Maybe I'm starting with the sequence 1, 1/2, 1/4, 1/8, 1/16, so on and so forth. Let's say that this is my sequence x. Then the sequence that I'm going to form here, starting with x1, is going to be just take the first element of that sequence and then give me zeros afterward. Then the second element of that sequence of sequences is going to be the sequence which is 1, 1/2, and then zeros onward. And then we can continue this process all the way down. And we want to show that this sequence converges to x in the little L1 metric. I give this problem for a couple of reasons. One, we need to get used to this little L1 metric, which is the D1 metric that I've been referencing up from before. And two, this is a sequence of sequences. That's a little bit tricky to kind of get your head around. Notice that's a different type of way you have to think about the problem than in the previous one. In the previous one, we were looking at sequences and then subsequences of those sequences. This here is not a subsequence. That's not what I mean when I say a sequence of sequences. I mean that this is a sequence x1, x2, x3, where each element inside of this sequence is itself another sequence. These are all other sequences, not referring to the kind of the meta sequence or however you would like to try and distinguish it from these other sequences that are given inside of this list. So the question is, how could we show that this sequence that is given here converges to x in the little L1 metric? Well, let's go ahead and talk a little bit about what the little L1 metric is here. This is the D1 metric that we've been talking about. We've talked about D1 in a couple of different instances. Let's go back maybe and see if we can see in our previous slide where we can refer to if we need help in finding what this metric is. So here we are. I'm on the last slide here from our previous pages. And notice here I have those little superscripts that I was talking about for little L1 before. And notice that here the D1 metric is defined to be given two sequences x and y, the sum as I goes from 1 to infinity of the absolute value between any two values in a corresponding slot in that sequence. So it's a distance between those two values and then added together. So the hint is, right, first of all, that these sequences need to be a little L1 so that these particular D1s are finite. So the hint I gave from before was that was because of the triangle inequality. I still encourage you to take a look at that in case you have not already. So let's see if we can show this. What we want to show, let's go ahead and do our setup first. We want to show that xk converges to x in the L1 metric. So what does that mean? We want to show that the distance 1 for xk, x, goes to 0. And we can use this if we would like. And this is as k goes to infinity. So how are we going to kind of spell all of that out? D1, remember, is this. I'm going to take these two sequences, take the sum as well, I'm going to need to use a different letter here. I'll use I as a sum as I goes from 1 to infinity of this sequence x of k, this ith element of that sequence, whatever that is, minus x of I, whatever that element is. And I'm going to need to show that this goes towards 0. So now that we've spelled out a little bit of what we're attempting to do here, we see now that we're trying to take an infinite series, whatever this guy is, and show that the values that are here inside of it, these absolute values of these differences here, we want to show that this infinite series goes towards 0. And that's again as k goes toward infinity. So sometimes I will use this little thing up top, on top of the arrow here to try and signify that it's not the I is going toward infinity or anything like that. I is this, I will describe it as a running variable for this summation. It's the thing that goes, I goes from 1 to infinity. That's how you know you're adding up each and every part of the sequence. To give a better picture, maybe something that would be useful is to say, okay, well, let's try and picture what x to the k looks like. We're going to have this is x1, x2, dot, 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 xk, and then zeros elsewhere. So something like this. And then here, x is just going to be the sequence x1, x2, xk, but you'll get to keep going past that point. Xk plus 1, xk plus 2, and so on and so forth. So here, think about it this way. I want to take the differences between corresponding entries in this sequence, and then sum all of those differences up together and say that those go to 0 as k goes toward infinity. Maybe there's a little bit more intuition here about what's going on now. Let's see what the difference between the corresponding first entries is going to be. It's going to be x1 minus x1. Well, that's going to give me 0 whenever I take that difference. Same thing here for x2 minus x2. In fact, that's going to be 0 all the way up to this kth term, which is, again, xk minus xk, and distance is equal to 0. Notice how that's going to differ once I start taking a look at this. If I'm now taking this xk value, this sequence, and subtracting this k plus first entry in x and xk, then I'm going to get that that is absolute value of x of k plus 1. Similarly, over here, I'm going to get that this is absolute value of x of k plus 2. And you can start seeing here that I'm going to start getting some values that actually do happen. So let's see if we can do a little bit of math on this. We'll go ahead and wrap this up here to the top to give us a little bit more space. Let's take a look at what this sum is going to look like. This is the sum as I goes from 1 to infinity of the absolute value of x of ik minus x of I. And we notice that this is going to, notice that these terms, first of all, just to kind of summarize what we've said from before, that this is 0 if I is less than or equal to k, and that this is x sub I if I is greater than k. Oops, if I is greater than k. That kind of summarizes what we were looking at from before. I should say absolute value of x sub I there. So using I here as our running variable, going from the first to the nth to the infinity type of term, then we see what we're going to be trying to add up here. So this is going to imply that the sum as I goes from 1 to infinity of these x of I is really can be shortened like this, or rather of x of I k minus x of I is going to be equal to the sum as I goes from k plus 1 to infinity of the absolute value of x of I. And we want to show that this goes to 0 as this k goes toward infinity. Now let's think a little bit about what's happening here. K is going toward infinity, which means, where is k in this expression? It's right down here. So that means that basically the number of terms that we're adding together, although it is infinite at every single step, we're cutting off one more term at the end of all of that. So here's something that I'm curious about, is can we say now that this value goes towards 0? Oftentimes in a real analysis course, we are told that this is the tail end of a sequence. This here is the tail end of a series, I should be saying. The tail end of a series is I've gone through and said I'm going to cut off maybe past a certain point, and we can call that k if we need to now. And I'm only looking at the things that happen around the tail of that series. Well, there's a neat little argument here, and I encourage you to take a look at this if you haven't seen it already, that says that if you have a sequence which is finite or a series that converges to a finite number, then exactly this value, this tail end of the series, has to go to 0 as the tail gets shorter and shorter, as you get closer and closer to the tail. I'll go ahead and maybe try and show up something here on the screen that kind of gives you a reference to that so that you can see that here. All right, I couldn't find a sufficient lemma proof in the reference I was going to try and give you. So instead, I just wrote one down myself for this same lemma to say that if this, you get a finite value for this infinite series, then the sequence, the tail ends of this series converges to 0. Notice the way that I do it is I split up this series in terms of an arbitrary value of k. Well, a series of infinite series can be broken up in terms of the first grouping of terms and the second grouping of terms. And you can always subtract over a finite number for any of these given k, and that's what you get to have right over here. And since now you can say, okay, now you're getting that this is itself kind of these are two equal sequences, hence the limit as k goes to infinity of these two things is going to be the same. And as long as you don't get something like infinity minus infinity over here, which would be an undefined term, as long as it's a finite minus a finite value, then you get that this limit of tail ends of sequences is indeed going to be 0. That might be something that we intuitively know. Just wanted to give a quick write down of where that proof kind of comes from. So given that proof, we now have exactly what we want to show, which is that this goes to 0 because this is the tail end of a series. Now, I have left over one thing, which is that I need to say that this series that I'm beginning with, namely the series I goes from 1 to infinity of x sub I, is finite. So I need this. But remember that the xi, where these things came from, were that these were the sequence elements inside of the sequence x, which is something in L1. The little L1, remember we said, are all of the sequences that are summable. That means that they have this property. So because this sequence is finite, we can say the tail end of the series goes towards 0. We may not have been able to say this, say if this had been the sequence 1, 1, 1, and so on and so forth, and we had been doing the same sort of process as we were doing below. Because now adding these two sequences, the sum between the difference between them is always infinity. So you never do actually end up getting to see them in this way. They never do get closer to each other in the L1 norm. I don't want to spend too much time here, but I do want to kind of introduce some other types of metrics that you might see here. This is a little bit of a tangent and aside, and I like to do this sometimes, and you'll see me do it several times as we go through this series. There's going to be some topics that I introduce for us that are going to be useful depending on where you might see them later on. You might have seen function spaces that are like big L2 or big L1 in other types of classes, especially if you have gone through a more applied context from before. But you might have also seen big LP, and you might be asking, are there little LP spaces as well? Even if you haven't been in that context, you might have noticed that with our definition of D1 and D2, we seem to have a very particular structure in how those things are formed. Namely, D sub P seems to be the type of metric that gives for a function x, right, its distance from x to 0, to be the sum as I goes from 1 to infinity of x sub I to the p, sum all those together, and then take them to the power of 1 over p. So this mimics the standard metrics on like D1 and D2, for example, if I wanted the metric to go like this. So in general, d sub p of xy, if I wanted to go through and write what that is, that would be the sum as I goes from 1 to infinity of x sub I minus y sub I in absolute value to the pth power, and then raised the whole sum raised to the power of 1 over p. I need the absolute values here. Otherwise, this sort of sum may not converge absolutely. Okay, so now the question is, does this work? Does this give us something that makes sense? Could we do this for all possible values of p? And that's something that's worth looking into and asking some questions about. Does this sort of thing give us a metric space? Now, this is certainly not at the level of trying to give it to you as a homework problem, because the hardest thing to show that this thing is a metric space is to show that it has the triangle inequality. And there's quite a few slides in what is here and what's to come after this that shows the triangle inequality for this. Now, also something interesting to note is that this is a metric space when p is greater than 1. Notice here, first of all, a few things. One, I'm not asking for this p to be like 1/2 on the inside and then 1/1/2 or squared on the outside. That's not typically where you see the context for these little LP spaces. You usually start at little L1, then you can go to little L2, little L3, so on and so forth. But notice also that this p greater than 1 is not saying that p has to be a natural number. This can be any number greater than 1. So what I'm about to introduce to you is a rather important class of uncountably many metric spaces, and they all are of the form little LP. What are they? They are subsets of the real sequences that all have the property that their notion of, so I'll define it for you here, so that this space, little LP, is defined to be the set of all real sequences such that the sum as I goes from 1 to infinity of the absolute value of x by raised to the p power is less than infinity. This is a whole class of metric spaces and can be done for any value of p. Notice that we're not going to get imaginary numbers because we're taking absolute values for our x of I. That is something that is important for us, is to have those absolute values, and was why I had to correct it here on this slide. It wasn't correct before. And two, the distance metric on this is now going to be a finite metric thanks to the fact that this value in particular is less than infinity. There's a little bit of a triangle inequality for real numbers that is used in that argument. But to show that this actually is a metric space takes a lot of work. Instead of going through each and every step here, I don't want to focus too much on this. I want to leave this to you as a resource to see that proving that things are metric spaces sometimes are a little bit more detailed than we would expect them to be. This sort of stuff is going to be very useful for you if you end up going into this particular realm. So I'm going to go ahead and make sure it's cataloged. You have it all here ready to go. And I'll go ahead as well in this video and describe a little bit about what's going on in each of these steps and what we're actually trying to do. I will go ahead and highlight real quick the things that we are going to be seeing later, so that you know these are the things to take notes on. Other than that, step back and watch the show. Those things are going to be the Helder inequality. This one is going to be seen later, especially in week 8. And Minkowski's inequality. This is the triangle inequality for these little LP spaces. Sometimes we will say, oh, this is kind of like Minkowski's inequality and how you go about and do this. So this type of proof that we get for this theorem is going to be useful for us later on too. So we'll use both of these two lemmas later on. We're not going to use them right now. We're going to use them more when we get to normed spaces. You may actually know that this is a norm type of notation that's given here. And I'm defining something that is called a norm, but we haven't talked about that yet. We won't talk about it for a while. We don't need norm spaces until week 8. But we can do all of this mathematics now with the mechanisms that we know from infinite series. And you'll notice here that there's a lot of infinite series, as well as just defining variables in specific ways that are useful for us, helping them break things apart. So all of the mathematics here does not require any heavier machinery than what we have available to us right now. It's just a lot. It's just a lot. That's the best way that I can describe it. Let me go ahead and show you a little bit before trying to make you too scared maybe of what's going on here. Let's start by saying, is little LP even closed under addition? Is it the case that if I take two sequences that share this property of having this condition, is it true that adding those two sequences together, term by term, does that give us something that is going to be inside of this space? So we'll start here. If you take any value p that is in between 1 and infinity, and any values of a and b that are non-negative, then first notice here that I'm not even going to say anything about sequences or functions or anything like that. I'm just going to say that this is something that is true for any collection of numbers, a and b. Then a plus b is to the p power is less than or equal to 2 to the p times a to the p plus b to the p is essentially what I'm trying to say. And then I'm going to use that fact to say that x plus y is in little LP given any two sequences, x and y, inside of the space of little LP. And the connecting piece here is that a plus b is less than or equal to 2 times the max of a and b. If a is less than b, for example, well, then if you just say a plus b is less than or equal to b plus b, then yes, absolutely, because we just started with a is less than or equal to b. We could have flipped around that inequality to get b is less than or equal to a, in which case a is now the max here, and that's why this inequality works. So if I raise both sides to the power of p, then I'm going to get a plus b to the p, my starting point, is less than or equal to 2 to the p, max of a to the b plus b to the p, and without loss of generality, I can get another less than or equal to sign by just adding those two terms of the max together, since, well, they're going to be non-negative terms anyway. So if x and y are both sequences inside of little LP, then now I can start doing this calculation. This is starting with something of the form x sub n plus y sub n, taking this to the power of p. Let's say here that these are all non-negative values just to kind of get us started off. Then this is going to be, well, absolute value here. Well, this is going to be less than or equal to, by the triangle inequality, x sub n plus y sub n, all to the power of p. And then finally, I can break those apart in terms of my formula, that this is 2 to the p times absolute value of x sub n to the p plus y sub n to the p. Here, my a is equal to absolute value of x sub n, and my b is equal to absolute value of y sub n. This is true in every single term of this series, and hence summing over all of these possible terms, since we have a comparison test we get to use here, this whole series is going to be less than or equal to this series that's given over here. Finally, we wanted to show that this value of adding those two series is finite, but we've gotten it now in terms of a linear combination of finite terms, in which case this is going to be less than infinity. But to show little LP as a metric space, we need a lot more strength in it, particularly this inequality, because yes, this is part of that little LP norm for the sum of x plus y. But what we want to show is this, right? We want to be able to show that the triangle inequality holds for this, that if you have dxz, that this is less than or equal to dxy plus dyz. And that's going to be very tricky to show, because looking at what these distances are defined to be, you're looking at something like this. This is the sum as n goes from 1 to infinity of the absolute value of x sub n minus z sub n to the power of p, and then to the power of 1 over p is less than or equal to, and now you're repeating this formula for each of x and y. And this is essentially why this becomes such a complex process, is that you're doing a lot of stuff with infinite series, but you're also playing around with the powers of each of the numbers that are inside of here. You're being able to break things apart in specific ways. That's a little bit tricky to try and figure that out. But the rest of this is going through and making that sort of process happen. Let me mention a few of the important points in how we're getting there. This first one, Young's inequality, says that there is a relationship between values of p and q. Here I am defining q to be the conjugate exponent of p. This might be a new term for us. The definition of a conjugate exponent is this. You're going to take the value of p that you're given here inside of little LP, and you're going to say that q, the conjugate exponent, is p over p minus 1. The reason it's called conjugate exponent is that it has a very interesting property. That is, that if you define this to be q, then 1 over p plus 1 over q is equal to 1. So there's some weird conjugacy going on here. The exponent thing is kind of coming from the fact that when you take two bases and look at their exponents and try and multiply them, that they add together. And then the conjugate is kind of this notion of kind of being in the denominator rather than the numerator. There's a lot kind of floating around here in terms of this term. But if you take those two terms and work with them together, then you can notice here plugging in q is p over p minus 1, that this is 1 over p plus, after simplifying, p minus 1 over p. So this is p over p, which is equal to 1. So that's the reason for the definition here for this q. And that's exactly how it's used down here. Let's take a look here and notice that given our definitions of p and q as conjugate exponents, that p minus 1 times q minus 1 is equal to 1 as well. A neat little kind of trick that you can work with those there, and you can check that for yourself. So the functions t to the p minus 1 and t to the q minus 1 are inverses. That's that conjugate exponent that we were looking at from before, for any value of t that is greater than or equal to 0. The picture on the left here shows that if you're looking at the rectangle for everything inside of the integral, or rather everything inside of this area from a to b, that's going to be less than or equal to the two following integrals added together. This one being a dx integral, this one being a dy integral. Here, this is the function x equals, or y equals x to the p minus 1. And if I wanted to go through and figure out what that integral was equal to, I'd get something like this. But then if I said I'm going to take this to be a dy integral, so looking at it from this side, then remember those integrals start from the y-axis, and these go from 0 to b. So that integral there is going to look something a little bit like this. Notice here that what I'm getting is something that is a little bit larger than the value of just the rectangle a times b. Note that this inequality becomes an equality only if a comma b is a point on the function. That is, if this point that's given right here is exactly on the function. Then if we solve what these integrals are, that is, if we actually take this integral, then what we're going to get for this first integral is a to the p over p, and that this one is b to the q over q, then we get a very interesting inequality that we maybe would not have expected, which is that a times b is less than or equal to a to the p over p plus b to the q over q. The equality part comes from the fact that you only get equality if a to the p minus 1 equals b, which is to say that this a comma b is a point on this function. So that would actually mean you get this sort of equality there. We only use that in a very small way here in the proof of Helder's inequality to talk about equality. In fact, here we may not even mention it, but it does have something to do with the fact of if these sequences are like scalar multiples of each other, then you could get a equality in what is to come here. But neither here nor there in this case. Let's say that we have p being between 1 and infinity. Here, p again is being defined as the subscript here for our space little lp. And then we define the norm of a sequence here, x in terms of this p norm, to be this value right here. You might recognize this as the distance between the sequence x and 0. Then if x is in little lp and y is in little lq, then you actually get that you get this little inequality right here, which is that you can bound what this is, which is here, this is taking two sequences and multiplying corresponding entries together, then taking their absolute value and then looking at their product in the D1 metric. So this is the sequence x sub I, y sub I, and this is the distance from that to 0 in the D1 metric. So there's a little bit of a process that goes along here. You can take a look to see some interesting things if you're curious about this, but the proof here is not that big of a deal. I don't want to kind of emphasize this for where we are at this stage. It does use Young's inequality at a particular point, and that's why we needed it before this lemma. But a neat little idea here. We'll come back and revisit this once we need this a little bit more in week 8. And then finally, Minkowski's inequality is the one that tells us that we get a triangle inequality here, namely that the distance from here, this is going to use it in terms of x plus y and 0 is less than or equal to the distance between x and 0, and then plus the distance between y and 0. This is a particular version of the triangle inequality that's being used, and in fact can be used to show that this thing satisfies the triangle inequality in terms of our metrics. Now, you may have been convinced in this already because you see this as kind of like the distance triangle inequality that we said right here. But just to make clear that we are getting this in the correct notion in terms of metrics as well, since we are just getting used to the metric here, I've gone ahead and given an argument as to why this is good enough to guarantee the triangle inequality for any given point that you might have, which is this dx comma z is less than or equal to dx comma y plus dy comma z, this notion of the triangle inequality that we're familiar with metrics. Notice here that I'm using some kind of interesting tricks. I'm using one trick that tells me that if I look at what this particular metric is defined to be, then the distance from x comma z is the same as the distance from x minus z to 0 for any two sequences x and z. So I'm using this neat little property there. I then use the property that we're defining here in Minkowski's inequality, at this stage, kind of replacing x with x minus y and y with y minus z. And once I get everything there put together, I can use that little trick again to bring the y back over and the z back over to get to this stage. Minkowski's inequality is kind of interesting here, so I want to talk about it a little bit. So notice here that although this does not refer to the conjugate exponent, I do need to write this here at this point in my proof, that q is equal to p over p minus 1. I will be using that at a particular point here, and that's going to be because I need to use Hölder's inequality. So the way that I'm going to need to start with this is to show that this value here, which I've defined before to be the exactly what we have over here on this left-hand side. The sum as I goes from 1 to infinity of x sub I, x sub I plus y sub I to the p, and then to the power of 1 over p. Notice that this is now going to be x plus y sub p to the power of p for that particular value. Then I can break this apart one factor at a time and take a look at this x sub I plus y sub I sub power to the p minus 1 here, and then do a little quick triangle inequality, breaking apart here the x sub I absolute value and the y sub I absolute value parts here. So doing a little triangle inequality. And then at this point, I have two things that are being multiplied together to find a distance 1 metric. That's because this is all the absolute value of something, this being of a particular sequence of absolute value of x sub i's, this being of a particular sequence of x sub I plus y sub I absolute value to the p minus 1. A little strange way to see this as an L1 metric, but it's because we're breaking apart these two parts into different sequences. And then Hölder's inequality says, okay, well, I can now just say this is the p norm with respect to this metric times something in terms of the q norm with respect to this metric, and using the fact that p and q are conjugate exponents. And then the same thing happens down over here. And then the last thing that I do is I do a little bit of working around with the definition of q to figure out that this is equal to this value over here. Notice now that I've got the thing that I want, the collectedness of the norm of x sub p plus norm of y sub p together, and that everything here, once I take a look at what this is after expanding out what q is, essentially, I'm going to get some p minus 1s to cancel in the result of all of that. And I'm going to be left with something in a norm sub p to the power of p minus 1. Finally, my last thing to do is to divide by those p minus 1 powers and get to something that's just in the form of the norm of x sub y sub p. And that's going to get me this Minkowski's inequality. So kind of just a neat little tangent here to show that really what the big deal is behind all of this is that, one, sometimes these sorts of calculations end up becoming a little bit trickier. I'm not the type of person to say these things don't exist. I'm not the type of person to say we don't have to worry about this ever. I am saying in week 8, we are going to get to looking at arguments like this. We're not quite at the strength yet that we need to be with metric spaces in order to be able to employ arguments like this effectively, perhaps at this stage. But this is something that I want us to see early on so that we can know where we're going. We can know where we're heading, which is that we're going to be seeing kind of some ways of working with series and looking at sequences in these particular sorts of ways. So the thing that we get to take away from this argument right now, so this is the main takeaway, is that little LP d sub p is a metric space. And that's basically it. We have to do a lot of work for that because we have to go through and see that the triangle inequality holds, which is exactly what we were doing up here. But that's really what we want to take away from this. If you're writing notes and that's the main sentence you get, that's totally fine from this last section. We'll now go ahead and introduce little LP in some of our homework problems just so that you know that you can kind of get to play around with it. The main thing that I'm going to have you playing around with it right now for is not even using conjugate exponents or things like that. I just want you kind of playing around with this formula, the fact that little LP is this particular set, and that the distance formula is defined in this particular way. So that's kind of the way that we'll be seeing these formulas at play. The most common ways we're going to see it are going to be in little L1, little L2, and this doesn't quite work with this definition, but little L infinity. We'll see that with these sorts of definitions. So just to be very clear about how that sort of stuff looks. But that'll do it for us today. We've been talking a lot about how to have sequences converge in a metric space. And notice here, we've been doing it in two different kinds of contexts. One context is very algebraic and one context very geometric. We saw how this kind of can work in a couple of examples, especially in this example where it turns out that taking sequences of sequences is something that we can do. So getting used to this sort of process is going to be important to us. We see how very important it is, especially in the context of LP metrics, as we have to do this sort of thing quite a bit. Dealing with various sequences and infinite series with regards to those sequences comes up quite a lot in this world of metric spaces. But that'll do it for me. Thank you so much. Have a wonderful day.